the time dilation formula. We ended the first video on the special theory of relativity with Einstein's postulate that the speed of light is constant and independent of the observer, or frame or reference. If you haven't watched the first video, I recommend you to watch it and then come back here. If you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. Albert Einstein, in his first work on special relativity, was convinced that light should travel with an absolute speed of 300,000 kilometers per second, regardless of which observer was measuring it. But what are its consequences? The first consequence is that two different observers can take different measurements of time for the same event. Let's see how it works. Imagine a wagon of height d moving with speed v relative to the ground. An observer, O2, is inside the wagon at rest in relation to it. A light source F is fixed to the floor of the wagon and a mirror E is fixed to the ceiling of the wagon. At some instant, the source F emits a pulse of light directed toward the mirror, and at some later time after reflecting from the mirror, the pulse of light arrives back to the floor. Observer O2 carries a clock and uses it to measure the time interval that this event occurs. Because the light pulse has a speed c, the time the light takes to travel from the floor to the mirror and back to the floor is given as follows. The subscript p stands for proper. This time interval is called the proper time. In general, proper time is the time interval as measured by an observer who sees the event occur at the same position as the event. The observer O1 sees the light make a path slanted to the right from the source to the mirror and then descend through a path also slanted to the right, symmetrical to the first, returning to source F, all within an interval of time delta t. Delta t is the time it takes the light to travel from the floor to the mirror and back to the floor. So it takes light half that time to go from the floor to the mirror and half that time to go from the mirror to the floor. Look at the triangle. The distance from the floor to the mirror is c times half of delta t. By the time the light reaches the mirror has moved to the right a distance v times half of delta t. To obtain a relationship between the time intervals measured by these two observers, it's convenient to examine the right triangle and apply the Pythagoras Theorem. We will rearrange this equation and solve for delta t. Pay attention. Since the speed of the wagon will always be less than the speed of light, then the gamma constant will always be greater than 1. So we see that the time interval measured by an observer that sees the wagon moving is longer than the proper time measured by an observer at rest with respect to the wagon. This effect is known as time dilatation. We may summarize this important result. Suppose an event occurs in a particular frame of reference, which we call the rest frame. The time interval as measured by an observer in this same frame is the proper time. Then an observer in the second frame of reference moving with constant speed relative to the rest frame will measure the time interval to be delta t. The relation between these time intervals is given as follows. The result shows that time measured in a moving frame is always longer than the time measured in a rest frame. Gamma is called Lorentz Factor. The Lorentz Factor and our Newtonian world. Let's look at the Lorentz Factor. If V is negligible with respect to C, then the ratio between V squared and C squared is approximately 0 and the Lorentz Factor is approximately 1. The time dilation is negligible and each observer measures the same interval of time. If V is less than C but not negligible, then the ratio between V squared and C squared is less than 1, and the Lorentz factor is greater than 1. In this case, we must consider time dilation. Length contraction. To understand length contraction quantitatively, consider a spaceship traveling with speed v from the Earth to the nearest star as seen by two observers, one on Earth and the other in the spaceship. The observer at rest on Earth, and also assumed to be at rest with respect to the star, measures the distance between the Earth and the star. This length is called the proper length. The proper length of an object is the length of the object as measured by an observer at rest relative to the object. According to this observer, the time it takes the spaceship to complete the voyage is delta t, and the proper length is v times delta t. The space traveler, using his spaceship clock, measures a time interval as proper time. The space traveler claims to be at rest and sees the star moving toward the spaceship with speed v, and the time interval he reached the star is the proper time. So the distance measured by the space traveler is v times the proper time. We replace delta t with the Lorentz factor times the proper time. Note that the product v times proper time is the length measured by the space traveler. Then, the distance measured by the space traveler is given as follows. Therefore, the distance measured by the space traveler is shorter than the proper length. This effect is known as length contraction. The length of an object measured in a reference frame that is moving with respect to the object is always less than the proper length. The twin paradox. An intriguing consequence of time dilation is the so-called twin paradox. Consider an experiment involving a set of twins named Isaac and Newton. Consider that Isaac and Newton live in a time when humanity has enough technology to make interplanetary travel with spaceships very fast. Suppose Isaac remains on Earth and Newton takes a spaceship towards planet X. Planet X is about 4 light years away from Earth. The spaceship is capable of reaching a speed of 0.8 c. After reaching planet X, Newton immediately returns to Earth at the same speed. Upon his return, Newton is shocked to discover that Isaac has grown older than him. First, let's find the Lorentz factor to make easier the things. Now let's calculate how long Newton's journey took from Isaac's point of view. Newton's round-trip journey will take 10 years. This means that while Newton goes back and forth, Isaac gets 10 years older. But for Newton, The total time of the round trip, decreases as a result of the high speed at which he moves. The distance to be covered by him will be smaller, and it's given as follows. Note that, in fact, Newton's path has gotten shorter, going from 8 light years to just 4.8 light years. Length contraction occurred. To cover this total distance of 4.8 light years, Newton took also less time. Pay attention. During the journey, Newton aged 6 years. Isaac became 4 years older than Newton, since for him 10 years has passed, while for Newton only 6 years. Amazing, isn't it? But these are the strange effects of a relativistic world we are not used to. The muon problem. An interesting example of special relativity involves the observation of muons. Muons are particles that can be produced by the collision of cosmic radiation with atoms in the atmosphere at an altitude of about 9,000 meters. Muons have a speed very close to that of light and have a lifetime of 2 microseconds when measured in a reference frame at rest with respect to them. First of all, let's find the Lorentz Factor. If we take 2 microseconds as the lifetime of a muon, and assume that their speed is close to the speed of light, we find that these particles can travel only about 600 meters before they decay. Look at the calculations. Hence, they could never reach the ground from the upper atmosphere where they are produced. Experiments, however, show that a large number of muons do reach the ground. How do explain this? The length contraction explains how. Let's apply the length contraction formula. As we figured, the muon would only have time to travel about 600 meters, but in its frame of reference, this is more than enough, since the 9,000 meters shrinks to about 570 meters. Can a muon be treated according to classical mechanics? No, it cannot. In the next video, we will start the study of relativistic mechanics.